I don't know.
Okay.
I got him. I gave him the. Okay, we are live.
Okay.
I cannot see it.
I don't know. Okay. Okay. We are live, but call.
Yes.
Okay, call.
Yes.
Entered, but he is out again.
I makes a. Hello, I warmly welcome you to our 23rd webinar by the Academy of Space Renaissance International. My name is Sabina Heinz and I'm the person responsible for our webinar series. And today I'm really delighted that you have come to join us. And I would like to present you our special guest, and I'm really happy that he is here now with us, Professor Gustavo Medina Tango from Mexico. Hello and welcome.
Hello, how are you? Nice to be here.
Gustavo will speak today about COLMENA, a new concept on lunar exploration. I also would like to welcome Adriano Ottino. He is one of our vice presidents, like me, and former president and founder of SRI. Hello, Adriano.
Hi, Sabina. Hi, Gustavo.
Hi, how are you?
Glad to have you here.
Normally, we have here in our round Cole Amagos. He is normally informing us about the news. But it looks like that his internet connection is not the best. This can happen. Maybe I tell you that we had a really amazing festival, Space Renaissance Art and Science Festival at the Eichenhold Observatory with many lectures. We had also Moon Buggy, and we had Astronaut Day and Space Day, and we had a Philosophical Day and an Art Day. And it was really amazing and was so nice to meet all these people. Unfortunately, I got coronavirus. I'm still not so in good conditions, but I'm going better and better day by day. Before leaving the floor to Gustavo, I would like to introduce him to our audience. Dr. Gustavo Medina Tango is professor at the Institute of Nuclear Sciences of UNAM in Mexico, where he leads the group of ultra-high energy cosmic rays and is the head of the Laboratory for Space Instrumentation, LINX, which he created in 2009. He has also created and is responsible for the National Laboratory for Space Access, LANE, in state of Hidalgo, Mexico, and which will start operation in 2022, as on this year. Maybe it has started already. And he was for 10 years the science coordinator of the International YEM-USO collaboration and member of its executive board, and as such he led the Mexican participation in the development of several instruments under the coordination of CNES, NASA, AC, and Roscosmos. He implemented a platform for stratospheric ballooning of small science and engineering payloads, which operates regularly from Mexico and has also flown in cooperation with CSBF NASA. He has been the PL and project manager of the NanoConnect 2 satellite and the COLMENA lunar mission. He has been professor at the Institute of Astronomy and Geophysics of the University of Sao Paulo in Brazil, and adjunct professor of physics at Vanderbilt University, USA, as well as visiting scholar of Riken Institute in Japan. He is also scientific advisor to the Secretary of Foreign Relations of Mexico, and he made his major in physics at UNT in Argentina, his PhD at USP in Brazil, and postdoctoral stays at IAG, USP, University of Cambridge in UK, and University of Leeds in UK. He is the author of 217 articles in scientific referred journals and more than 500 conference papers with more than 2,000 citations. So, normally I would say Gustavo, the stage is yours, but now we have Cole. Let us allow that he has 2 minutes to read the news, the space news, the latest, and then I give you the floor. Cole, just
thank you, Sabine. Sorry about that. I was having some connection issues, but I think they've been resolved. I'll just quickly share my screen. Share. Okay, so just for a quick overview of exciting developments in recent space news, the United Arab Emirates announced a new fund package for their space program. It was over $800 million, and it's intended both for the space program and to develop a small radar satellite constellation. The satellite constellation is intended to operate in the X-band, and while that the number of satellites in the constellation has not yet been released, the first satellite will be launched, or is intended to be launched in 2023, with the last satellite of the constellation intended to be launched in 2026. In some more space policy news, Saudi Arabia recently joined the Artemis Accords. They're the 21st country to do so. And this is developing on the 8 original signatory countries. In a press release, a NASA administrator cited it as a commitment to the responsible, peaceful, and sustainable exploration and use of outer space. And what I thought was particularly interesting was, in terms of just the language of the report, the NASA cited humanity's rapid expansion into space, which is what we're all here for. So that's all exciting. In news back in Texas, SpaceX had some launches, some landings, and a fire. A record-tying 13th mission was recently landed for a Falcon 9 rocket as of yesterday. And this was preceded the week before by a static fire test of the Starship booster that is pending a much anticipated launch license for August. The static fire ended in an actual fire at the bottom of at the base of the platform, and the damage to the vehicle is still unknown to the public. It's currently undergoing repairs at the production facility, and we still have no launch date as far as I'm aware for the Starship Booster 7. Still pending the 75 measures to be taken after the FAA environmental investigation. In other news, the first images from the James Webb telescope were released on July 12th. They gave some really exciting results, and already a Jupiter-like exoplanet over 1,000 light years away has been identified as having water, and as well as possible clouds in its atmosphere. And this isn't the first time this has been discovered, but it is exciting that this has already been discovered, given the data was only released a week ago. And Hubble didn't. I think the first time Hubble discovered water on a planet was in 2013, or on an exoplanet was in 2013. The telescope was struck by several micrometeors for several months, but the report on the damage from that wasn't released until July. The damage is apparently greater than they anticipated. They allowed for some micrometeoroid damage, but the rate and scope of these micrometeoroids is apparently greater than they initially planned for. So the telescope is projected to last for 20 years, but given this, they're worried it may not last quite as long, but only time will tell.
Can you make it shorter?
Is a wrap for today.
Okay. Okay, thank you so much. Thank you for this presentation. Can you stop sharing the screen then,
I can.
Gustavo? Okay, thank you. Thank you so much, Cole. And now, Gustavo, the stage is yours.
Okay. I should be sharing now, am I?
Yes.
You are sharing, yeah. You are sharing.
Okay. Well, thank you very much, Sabine, for the invitation. It's really a pleasure to be here and to know the SR Academy. And well, without much ado, let me go ahead. So I will present today a little bit about COLMENA, which is our lunar mission, and we consider as a new concept for lunar exploration, and we think probably a tool for Mexico eventually for an effective participation in this new era in space. I don't know very much what is the background of all the people that could be there, so let me invest some time in giving context and background. So as you all know, space is changing fast, especially due to miniaturization and new technologies and regarding payloads and disruptive new launching capabilities like recovering of rockets, as has just been mentioned in the news by SpaceX. And this is having profound effects. This is producing a revolution in access and to space and also in space technology, and therefore a revolution in actors, basically with the lowering of the threshold, the financial threshold to enter in the sector. New actors like us, small actors, are able now to participate of this process and also to produce new kind of applications and services. Today, this is very evident at LEO, at low Earth orbit, but soon it will be also evident in which says regarding to the moon and probably to near Earth asteroids. I mean by that asteroids to which are very near the orbit of the Earth, and we can do a return trip there in around 1 year. Yeah? Emblematic of all this process, and also a trigger, if you want, for whatever is happening beyond low Earth orbit, is Artemis. Yeah? Artemis, led by NASA, but also gathering more and more countries in that push lately, has a comprehensive plan to go to the moon and to go to the moon to stay, yeah? To really build infrastructure, orbital infrastructure around the moon, but also surface infrastructure to create a permanent presence on the surface, and also eventually to develop the building capabilities and blocks for Mars missions and eventually to asteroids and other places of the, at least of the inner solar system. One main element of this thing is the gateway, of course, this orbital space station that will be there hopefully in the next horizon, the next few years. But it's not the only thing, even if it is the more visible probably, but there are the important pieces of infrastructure that have been developed, like Lunanet, which is, say, the internet for space, which is a disruption-tolerant network that will be able to really introduce the connectivity to the endeavors that will be produced in the moon, in low Earth orbit, and even eventually to have the capability to extend all this internet and connectivity to all the inner bodies in the solar system. And therefore to start to create a space of communication for science, for economy, etc. It is worth noticing that it's not only Artemis and its associate countries that are in this endeavor, but also China is going there as a very important independent player. Has performed a lot of missions and have produced some emblematic photographs like this, in which you can see from the Earth-Moon Lagrangian point 2, taken by the Keikiao relay satellite, this image of the moon and the Earth. And this is a fate really of the Chinese program, which is very comprehensive. We see several missions, 5 important missions already done and successful, including orbiters, lander, rovers, relay satellites, both in the near side and the far side, sample return missions. And also there is a sample return mission program already for the far side and the South Pole, 2024 initially. Also another very complex missions with orbiter, relay satellite, lander, rover, flying probe, etc. to the far side and South Pole, which is Change 7. And Change 8, which is also interesting, is the first in situ research utilization mission that will include even, in principle, 3D printing with materials extracted directly on the moon. And eventually a lunar base of 60 tons for the 2030s. And these are complex missions, really. So all are pushing very hard for these objectives. So the moon will be busy in the next few years. But what can we do in the moon? Well, several things. And science is one important aspect of that. The moon is very suitable for physics, astrophysics, chemistry, planetology, solar system origins studies, and evolution, biology, medicine, in situ research utilization, etc. Specifically for physics, which is my main area of interest, the moon has a unique potential. It has vast uninhabited spaces, and if there are here people that do research in astroparticle physics and ultra-high energy cosmic rays, for example, will know that vast areas are really a plus, with detectors of tens of thousands of kilometers probably. It has isolated craters, very low seismic noise compared to Earth. It has a very better vacuum than at any Earth laboratory, large cryogenic environment freely available, no significant atmosphere or ionosphere. One side is always facing to the Earth, while the other farther hemisphere is shadowed behind from the human radio noise. It is far from the Earth, but not too far as to be inaccessible, or to be probed by LiDARs, for example, from the ground on Earth, or to produce Cherenkov signals by skimming ultra-high energy cosmic rays or neutrinos that can be detected at Earth. Let's see some very few examples. One is radioastronomy and cosmology. Yeah. The lack of an ionosphere, for example, allows the deployment of surface radio arrays capable of interferometry at low frequencies below 30 megahertz. This is very important for cosmology, for the study of the dark ages, that is the period between the emission of the cosmic microwave background radiation and the formation of the first star and galaxies. Additionally, the far side of the moon is shadowed from terrestrial background. Therefore, it can be used as a region to study very small radio signals and very small perturbations, for example, to the 21 centimeter H1 line, which are expected to be a treasure trove of information of the thermal history of the universe. And in fact, can study the region between redshift 6 and redshift 150, which complement very well, for example, the James Webb Space Telescope measurements, which include only regions probably below redshift 15. Yeah. Another important potential is for gravitational waves. On the Earth, an important source of background that limits the measurements of gravitational wave detectors are seismic noise and Newtonian noise. On the moon, since there are no ocean tides, there are no winds, no man-made sources, the noise can be reduced by a factor of 1,000 with respect to the Earth. Also, the vacuum on the moon is 1,000 times better than in the vacuum tubes of the better gravitational detectors on Earth. Yeah? The LIGO-Virgo-CAGRA collaboration, for example, is able to observe gravitational waves above 10 Hertz. The future LISA Space Observatory will be able to observe below 0.1 Hertz. So this means there is a gap in gravitational wave observation between 0.1 Hertz and 10 Hertz that no instrument can cover. Well, that gap can be covered from the moon with moon observatories. LION is a good proposal, an example of that, which proposes basically to put a triangular array of laser interferometers inside the crater in the moon. At the bottom of the crater, when it is at very low temperature, very stable, you can have temperatures of up to 30 Kelvins, and 50 Kelvins will be okay for these detectors. Yeah? And there you can have, for example, if you take the Shoemaker crater at 88 degrees of latitude south, you can put an interferometer of 40 kilometers of sight inside the crater without problems. But there is not only science. The moon has also valuable resources like water, rare earth, aluminum, thorium, uranium. All these are elements important for technology, even for energy production. And also, eventually, whenever we are able to produce fusion reactors, helium-3, which is also probably there in sizable quantities, will be a very, very interesting possibility. Yeah? And there is water not only inside the deep craters at very low temperatures, frozen there. There are observations also that point to sizable amounts of water also in the sunny sides of the moon, that is more or less everywhere in the surface, even if at much lower quantities. For example, 100 times less than you would find in the Sahara Desert, but still at 10 to 1,000 parts per million. So this means that from a cubic meter of regolith, you still would be able to extract, I don't know, something like half a liter or something like that. For you to have an idea, these are neutron emissions from the poles of the moon, and the blue and purple regions are regions where you may have indications of rich deposit of water covered by dry regolith. So there will be scientific exploration that's guaranteed. That's the part we are always accustomed to in space. But also, it is almost unavoidable that there will be commercial exploitations, at least in the Earth and the nearby asteroids, these asteroids that are more or less with the same orbits of the Earth. In fact, a single asteroid, and we are talking an object of a kilometer in diameter, can have between 150 billion US dollars to $1 trillion US in precious metals. So asteroid mining is not an if, but a when. Sometimes I think whether we are not living anew in a 1491 scenario in which we are very soon to incorporate a sizable chunk of land to our universe, yeah? Like a new continent, the moon, but nobody is aware still, or most of the people is not aware that this change in society, in economics, in culture is ready to take place. And it will take place, if not tomorrow, in a decade or a few decades. So we have so many things to be done. One can ask, who will do this work? Yeah? Who will be the workers? Of course, human beings as astronauts will do part of the work, but human beings are not really very well adapted to all these environments, which are in general without atmosphere, like in the moon or asteroids, and completely exposed to radiation, the solar wind, ultraviolet radiation, and severe changes of temperature, and much different gravities, lower gravities than on Earth. So robots will be for sure one of the main tools. One approach is to have really very complex machines, whether anthropomorphic or not, that can have dexterity, even eventually possibly generate artificial intelligence whenever we are able to reach that point. And these machines will be very adaptable, will be hopefully generalists that can tackle several problems, problems that were not prepared to attack, and with a very large dedication of time, very, very low test time. But on the other hand, as they become complicated, they will be very complex and fragile and expensive. This means they will be massive also, therefore not suitable to operate at very low gravities. And for example, if we are on an asteroid of 1 kilometer in diameter, the gravity is 1/1000th of the gravity on Earth. And also they will have a rather high energy consumption. So this is one possibility, and that for sure will be used, but these problems open the opportunity for other alternatives to this. And one alternative, even if a humble one, is the approach we are trying to develop here at the Laboratory of Space Instrumentation. which is basically, instead of trying to focus on a very complex system of which we have a very small number, but are extremely versatile, use the other approach that the nature had been using for tens, or if not hundreds of millions of years, which is use small machines, small insects, not extremely complex, each one, if taken individually, not very powerful if taken individually, but when you put them in numbers and you make them cooperate and work toward a common objective, then they can do marvelous things. Yeah, basically all the soils we use for agriculture have been produced by insects, by small insects. Pollination is done for that. The forests are recycled basically by ants. So this can be an approach, and this is the approach that we are developing with COLMENA. Actually, COLMENA is the pathfinder of this pathway that we are trying to develop, which is using cooperative micro-robotics as a platform, as a complementary tool for interplanetary exposed surfaces, either for exploration or for exploitation. Using many small units but working cooperatively have some advantages in many scenarios. First, you have the capacity of self-organization. It's a complex system. You have a low cost per unit. You have simplicity, therefore you have robustness. Robustness because of the simplicity and also because of the low cost, because then you can send many more units that you really need. And if you start losing units, you can still do your job. It probably will require just more time, but it will be accomplished. Also, they are suitable to work in low gravity environments without problems. And of course, as always in life, there is a drawback, which is a specificity. That is, these machines, when you prepare an ensemble to do some kind of task, it will just do that kind of task. It cannot, and it can achieve it in a very adaptive way in the scenarios you were unable to predict, but it is this task. But they will not be able to perform other tasks. Yes, bees will not collect leaves in a forest. Yeah, that's it. But you have all these other advantages. So therefore, it can be a very good complement to work in these environments. So in this first mission, we are sending 5 units to the moon. We will put them in the surface of the moon. They will start their operation with a random configuration that we cannot predict. And then just by pumping energy, having interaction laws that are predefined and giving time to the system, they will have to do certain tasks like navigation in the system, clustering, that is, they will not only have to navigate in the regolith, which has not been done at this scale. It's completely different to navigate when you are so small in the regolith. I don't have time to explain the details, but the regolith will behave completely different, like a fluid or something like that. Also, there is no GPS for navigation, etc., etc. Well, anyway, they will navigate, cluster, and therefore this is the part of the mission which we'll say is they are the engineering objectives for the main pathway we have of developing this strategy of small units as a tool. But also they will do science, and they will study the limit layer between the surface of the moon and the plasma on top of it. The surface of the moon is covered by regolith. Yeah. Regolith is kind of a sand, is a dust with sizes of the dust grains that are typically on the order of some tens of microns. This means that the median is around tens of microns, but the distribution of sizes has a tail to very, very small sizes that go even to probably to nanometers. Yeah, this is because in the moon there is no liquid water. There is nothing that would stop the process of fragmentation of the dust grains, so they can become very, very small, extremely small. On the other hand, there is no atmosphere on the moon, no permanent atmosphere. So you have the solar wind arriving to the surface, and you have ultraviolet radiation arriving directly to the surface. This means that the surface will be electrostatically charged. And so you will have electric fields, yeah, from the surface of the moon. This implies that the smallest dust grains are able to float in these electric fields. Yeah? They levitate. They will levitate at different heights, but there is a particular scale that is of interest here, because this dust, in going up, will mix with the solar wind, which is a plasma, and we will produce a dusty plasma. Yeah? And this dusty plasma is characterized by the Debye length. That is a characteristic length in which charge is neutralized. So this dust will float typically mainly to this scale of the Debye length, which is more or less very near the surface, around a few tens of centimeters. So 20, 30 centimeters, something like that. We don't know exactly how much is it. Inside this layer, the regolith is floating, is moving. There is a large dynamics inside there. You can think that you are behind something like clouds of dust, and it's raining dust. And this thing is real. It has been measured. It has been observed, not measured, but it has been observed. For example, here on top, you have images from Surveyor 6 in the decade of the 60s, which is a photograph of the western horizon in the moon after a sunset. And you can see, you have this line that divides the lunar surface from the sky. And in the middle, you have this very bright line, which is thought to be light scatter, but this layer that is in levitation, yeah, between the surface of the moon and this layer. Yeah? So if you are a large machine, like the rovers you are used to see on the moon nowadays, or you are an astronaut, all these things happen in your shoes or in the lower part of your wheels. But our rovers have only 2 centimeters in height. Actually, all the electronics is at just 1.5 centimeters from the surface of the moon. So they live inside this kind of atmosphere, if you want, inside this dusty plasma. So for them, the habitat is completely different of the machines you typically see there. So this means that to do this micro rover is not the same as picking up a large rover and just scale it down. Yeah? All the physics change. You have to design anew completely. This will affect the operation of sensors, telecommunications, locomotion, the survival of electronic components. Abrasion will be a factor for all your mechanisms and motors. You will have dust blanketing on top of the solar panels, and these are all problems that have to be solved and studied when you work at this scale, and this will be a problem peculiar to these micro rovers. So at the science objectives, we will do measurements of the dusty plasma. We'll characterize it inside 1 Debye length. We will measure several parameters like temperatures, currents, deposition of dust in the dynamics they have inside this layer. We will measure magnetic fluctuations between 1 Hz and 200 kilohertz. So we will try to characterize magnetohydrodynamic waves that are propagating in this dusty plasma near the surface. And we will use different radio frequencies to try to study the total attenuation cross-section, the average size of these dust grains that are levitating, which is unknown, the average density, which is unknown, the dielectric content, and the Debye length near the surface. We produce the payload, but we are using as our lander, the Peregrine lander from Astrobotics, yeah, which is is a company, yeah, from US, from Pittsburgh. So they will take us there like an Uber. if you want. We will launch in the final quarter of this year, 2022, probably around November. We are not very sure yet of the final launching date. The landing will take place between 40 and 60 days after launch at the Lacus Mortis at 44 degrees north latitude. This is a very challenging region for us because it is a transition region between highlands and Maria, and therefore it is very difficult to predict what will be the properties of the regolith in this region, because it may be a mix of both types of regoliths, or there may be patches and we can come in one patch or another. So it's another additional challenge to this. Conceptually, this is the lander, the peregrine. We have these elements in the payload. On the one hand, we have the TTDM, the telemetry, telecommunication and depletion module, which is also a communication-based station between the rovers and the lander, and between the lander and the ground. We have the deployment mechanism, which is basically a catapult. Yeah? So we will eject the rovers from the lander, so the 5 rovers, which are the other element. We have this catapult for 2 reasons. The first one is the rovers are so small that they have no batteries. The batteries will not survive. So they work essentially, besides an emergency energy system, they work with direct sun. So if they were deployed on the shadow of the lander, they could stay there forever. They could die. So they are thrown far away. So we are sure that they are in the sun. And also we assure us in that way that they will start the operation in a random configuration that really we cannot predict. And this is important for our engineering objectives. The total mass of all this is only 608 grams, the 5 rovers plus the TTDM plus the deployment mechanism. Each rover has a weight of 56 grams. It's 10 centimeters in diameter, 2 centimeters high, and it has a single PCB where all the electronics is there, power conditioning system, emergency power supply, onboard computers, several sensors. It has even a radar, magnetic field sensors, emitters and receptors, 13 different frequencies, gyroscopes, telecommunication systems, independent motors, etc., etc. And it's also reversible. It can work one way or the other, because since we are throwing them with a catapult, we cannot even predict how they will fall. So there are 5 of these. The TTDM is this mechanism that you see here. This is basically a catapult. This is the arm of the catapult. And it has this container where the rovers are located, and from launch, during cislunar transportation, and during landing, and until they are deployed. Yeah? Well, here you can see a little bit how is it, and how the rovers are accommodated inside the system. So it has its own electronics, triggering mechanisms, communication systems, data processing systems also for the rovers. All our payload COLMENA is located on the lander. This is the peregrine lander. It has decks around its equatorial circumference. So we are here in one of the decks. From there, the rovers are deployed up to a distance of around 10 meters, where they start their mission, which basically, here you see a simulation. They will start their navigation, communications, etc. This is very much accelerated. This is accelerated by a factor of 225. These are very detailed simulations, actually. It's each one of these rovers in the simulation has all the mechanics, all the electronics, and the code really for navigation is programmed in a simulated embedded microprocessor there. Yeah? so basically, and this is the preparation of the rover is done with this simulation software and also alternating with operation in Regolith simulant. So this is how the COLMENA payload look like. This is the whole COLMENA already mounted with all the rovers inside. But it is not in the arm position, it is in the extended position. It is only armed near the moment of launch to avoid the stresses there. This is one of the small rovers. This is 56 grams. So it's more or less say a little bit more than 9 grams of weight on the moon. 4.5 grams per wheel. This is one of the problems for navigation because the regolith with such a low pressure does not compact, and it is electrostatically charged. It will behave like something akin to a fluid, but not exactly like a fluid. And here you can see how it would look like just before ejection during the deployment. Yeah? This is the suite of rovers that were prepared. So this was finished in October 2021 after almost 5 years of development and testing. And it was integrated to the deck of the lander in November 2021. Yeah? And now in August, probably, we will do the arming of the catapult to the compressed position. Yeah? And at that point, the timer starts to run for launching. So this mission profile, well, this is the first part of the profile during flight. Doesn't matter very much. So we go to the profile on the moon. This is one lunar day. Yeah, the diurnal part of one lunar day. So we will land in the morning, like say around 8 in the morning, more or less, to have an idea lunar time. And then after some hours, whenever we have reached a certain temperature, because the sun has been warming us, more or less around noon, a little bit earlier than noon in the moon time, we will deploy. And then during the first few hours, we will do all the engineering part, which is, well, turn on all the mechanisms, all the systems, see that everything has survived, start to do navigation, create, say, a coordinate system for navigation. This is something that all the rovers will do autonomously. We don't have control over them. We just observe what they do. And then they will try to navigate to choose among themselves a suitable point for gathering, and they will go and gather there and do some measurements of all this process of navigation and all the problems they encounter while navigating. After that, they will go into science mode, and they will start to do measurements from the limit layer of the dusty plasma on the surface of the moon. And they will do that for the remaining of one of this first lunar day. And then they will be turned off during the night. All the mission actually lasts for 1 day for all the payloads that go in the lander. The lander is taking something like 20 payloads. All will work only during that first day. And then possibly at the start of the second day, the lander will turn on just to check their own subsystems and survivability. And we will try to turn on also just to see if we survive the night for engineering purposes, but all the mission was already done. As I said, this is a pathway toward developing a practical tool that can be used for different activities and with different payloads. So COLMENA is the first mission. We are just studying the basic proof of concept of miniaturization in space and in this regolith surface exposed to the medium, and see whether what are the problems that really appear when one is there. For example, the rovers cannot have, due to their low mass, they don't have thermal control. They cannot have, say, heavy shielding for radiation. And they are really exposed to ultraviolet light. Also, vibration can be an issue in such a small thing during launching and moon landing, etc. And also during navigation, the interaction between the systems and the regolith can present very unexpected problems. So all this would be discovered by COLMENA. The second mission is Moonworm. We are already working on it, actually, at present. It will have new communications, a completely different structure for the rovers, with a more organic structure. It will have actuators and electronics integrated in the structure also, a new energy power system, a different spatial positioning and navigation system. And the third mission would be Moon Scouter, which is, we hope, the final structure, version 2 of this organic structure. It will be more a kind of a generic platform, payload platform, where you can prepare and assemble rovers for different tasks just by changing payloads. It will include chemical sensors and the capacity of data gathering and of the transport of materials from one place to another. And we will test long-term survivability, which means that they will work during the day and hibernate during the night and restart working during the following days. And that for a long period of time. And they will really test the capacities of working as a swarm. Another important thing of this mission is, and this is typical of this large transformation we are living now in space, is that this has been done all by students. All this mission along the almost 5 years of development have been done by more than 200 students. Here you see just 1/8 of the team because students come and go. So it's not the same students along the whole project, with the except of a few ones that have been there more or less constantly. And anyway, with this, I will stop and see if you have any questions. Thank you.
Thank you so much, Gustavo, for this interesting lecture. Can you stop sharing your screen? Then we can see you. Yeah. Yeah, it was really, really interesting. And I have some questions. Maybe they are stupid questions, but I'm not a scientist. I'm an artist. But if they are not really heavy, can they not blown away this small robots?
Well, fortunately, there is no wind, so they will not be blown away. But the fact that they are so light, yes, it presents several problems. During launch, especially, since all the mass has been diminished to the maximum, as you know, the rocket will vibrate during launch and will vibrate the load. So the thermal, the vibration envelope can be a serious point to consider and in a mission to mission, case by case. Yeah, we have developed actually most of the, I would say half of the time of the development of the mission has been related to try to solve problems with vibration with such a small mass. Yeah, because things can really break apart. And as you know, this is a catapult, so it is compressed, so it has mechanical energy inside. Yeah, and it is a flexible structure just because it is a catapult. Yeah, it is like a spring. So if you put this thing to vibrate, then it is really a challenge from the mechanical point of view, and especially when you have shocks also during launch. But then the other problem is once you are there in the regolith or on the regolith, when you see the regolith is dust, yeah, but it's a very special dust. is a dust that has been produced very different than the dust that you produce on the Earth. On the Earth, you have, in general, aeolic erosion, yeah, or erosion by tides when you have the sands in the beaches. So you have things that are going around, yeah. So the grains tend to be rounded, yeah. And you always have water here on Earth, liquid water at some point. So you start to produce smaller and smaller dust grains until they dissolve, and you have a cut. So you don't have grains that are too small. When you go to the moon, you have water, but it's not liquid and it's not enough to have a solution. So you form this dust by fragmentation. You basically are permanently impacting with micrometeorites and with high energy ions from the solar wind, and you start to fragment and fragment. And there is no limit to this fragmentation process because there is nothing to stop it. So you have very, very small dust grains. But on the other hand, since you are producing them by impact and fragmenting, they are not round. They are more akin to broken glass. Yeah. So you have points and arists.
Yeah.
So these dust grains are very peculiar. If you put a heavy weight there, they will do like this and they will lock. So immediately when you try to push them, for example, if you have to put the flag, yeah, you will not be able to, because when you start to compress, the dust will compress and will be rigid completely. Yeah. This means that if you have wheels and you have a large rover, like the moon cars and things like that, you are okay, because you put all this weight, the dust compress, and you have a solid ground to go around, and you will have traction. But our rovers are 56 grams. So this of mass. So in the moon, they are, say, rounding numbers, 9 grams. They have 2 wheels. They have 4.5 grams per wheel of pressure. So the dust will not compress. And now, the small dust grains that are on top of the moon are electrostatically charged. So the ones that are very small, they just go up and float. This is the layer I'll show. The others that are a little bit heavier don't fly, but they are loose. They are repelling each other. So this means this is something that is not a solid, is not a liquid, but is something in between. Yeah. So you are really navigating there. So the wheels of our rovers are more similar to these boats you have in the Mississippi that have these wheels with these flat surfaces to push. Yeah. So they do something like that. And we will test how they move there. But this is really a challenge since they are so light.
Yeah, that sounds challenging. Therefore, I asked this. And I have another question. You said it's only for one day, this mission. But can you not make some that they are recharge as a reusable, that you can recharge it? Because you said you push them on the Regolith, and then they start in the morning to load, and then they start to work. So can they not recharge or reload their energy? Is it not possible to make it this way?
Yes, actually, if they survive the night, they will turn on and keep working. The problem is that the lander will be turned off, and we don't have direct communication between the Earth and the rovers. So if the lander is off, they will be there around, and they can be there for a lot of time going around. Yeah?
Maybe you find a solution for this, because it's a shame to make all this work for one day.
No, but this is one of the important things of this new transformation that you have in space. When we have an objective, which is extremely specific, and this to test the navigation and all the problems that will appear in the interaction with the regolith, to test that they survived in the travel, the launch, and the landing, and whatever, and then to do these measurements in the regolith. Yeah. And these measurements are completely done in one day. So we don't need more. What this allows to us to make the mission cheap. because otherwise it would be extremely expensive. For example, the navigation part will only last for 3 or 4 hours. Yeah? And in that 3 or 4 hours, we can measure all we need to measure. If I do that, I can use motors that are not space qualified. These motors are so small, they are 1 gram, more or less, in mass, yeah? That really, it doesn't exist motors of this type that are space qualified. So if I want to be there during several days, for example, I need to change the motor by motors that are space qualified. They should be designed, developed. They will take several $1 million per motor just of development. And then each motor will probably cost much more than $1 million. So this is the thing that allows us to do a very complex mission very cheaply. And this is the thing that opened the gate to small entrepreneurs, to the academia, to do things that are significant, that can be developed into a result, but at a cost that is much, much, much smaller than what NASA would do. For example, the small helicopter of NASA in Mars, which is beautiful, is like this, and it costed $85 million. Our 5 micro-rovers with all the mission cost a factor of 100 or 200 smaller than that, yeah? Then we can do it. So it's basically you qualify the things and you design exactly for what you need. And basically, if something goes wrong, it was so cheap that you can try to redesign and do a second mission, instead of doing something very costly and try to eliminate the risk to 0 in order to have something that will last a lot, for example.
And
I think
just a second, and they are still packed. Also they are packed and waiting for the mission.
They are packed and waiting there in a clean room since several months.
Adriano has a question. Adriano?
Yes. I think you tested your devices with some kind of simulant of a regolith on Earth in order to understand if they were working properly. And I had some experience with the simulant of regolith at the premises of Enrico Dini in Italy. I think maybe you may know him. He's the inventor of the 3D printing for building. And he made a project with ESA some 10 years ago, 3D printing a piece of wall for a moon habitat. And yes, I saw what it looks like, at least a simulant of the regolith that was taken from a volcano lake in Italy. And it is, yes, an extremely thin powder that is also very dangerous, because if you breathe it, it's very dangerous for the lungs. And another comparison that comes to my mind is the powder of coffee, because in my life I was working making software for industrial automation, and once upon a time I had to work for a company making coffee machines, big coffee machines, and trying to batch a dose of coffee, trying to make a volumetric dose batching, then trying different ways to make batching. And all of my tests that try to use a mechanic, I don't know, something like a fan or something rotating, and it gripped, and it because that powder was so thin, and also oleous, because coffee is oleous, that nothing can spin more than a few seconds. Then stop it. So I have an idea of what could be to work with such a thin powder, and I think it's a really hard challenge, because yes, the only thing that I can imagine is that these small machines with two wheels will try to move inside this the regolith, and for instance they cannot advance, because it's like when you try to move with your car in the snow, for instance, no, and you try to move, but you sink. Yeah, you think well, I don't know. For sure, you have made some tests, and you have proved that this thing can move in that environment.
The first thing is that's why it is so difficult to do a good espresso, and Italians are the best for that. Anyway,
yes.
But yes, you have these kinds of problems, and the problem with the simulant of regoliths is that it is very difficult to do a simulant that is able to simulate all the characteristics of the regolith. Yeah?
Yes.
So basically, you not only have to reproduce the material. Fortunately, we have lots of volcanoes around, so we found the right kind of lava to do that, representative of these regions. But then, if you want to reproduce the mechanical properties, you are interested in the shape of the dust grains. Yeah? If you want to see also where to reproduce the shape, in which range of sizes. Yeah? For the wheels, there is one size of ranges that is really important. But if you want to go to the part of the propagation of electromagnetic signals and interference with all your electronics, then you are interested in very small grains. And then you are interested also in the shape of these small grains that will be charged electrostatically and will become dipoles. Yeah? Not to mention that they are radioactive also, because they have been bombarded permanently by ions. So it's very difficult to have a single regolith that is able to produce all that. And then to test it, electrostatically charged with ultraviolet light in vacuum. Yeah? Because of course, if you want to work with very small dust grains and you charge them electrostatically to the level they can levitate, you need to put strong ultraviolet light inside the vacuum chamber, but then you need to produce electric fields there. And then you need to try to not to destroy the pumps of your vacuum chamber with this small dust that will go into the pump and destroy your chamber. Yeah. So what we do is to do several kinds of simulants. For example, for the gross part of navigation, we prepare 18 tons of simulant, and for that we use the mining company directly and the miling of the mining company. This is a more, say, rough simulant, but it's mechanically significant.
It has to be classified by several nets that let pass some small grains,
and this is even
keep the bigger one, and so on at several stages.
And this is even for this large thing, but then you do it industrially, and you do it only in a certain range of sizes, and you try to reproduce the distribution function of size. But then if you want to test the specific things, like for example, the fact that we not only have the motors have gears for reduction of velocities. So they have gear inside. So you need to test now the very thin powder, and this is very difficult to produce. So for you to have an idea, with the best mechanical regolith we have produced, we produce only 8 kilograms instead of 18 tons. And we have 8 people working during 6 months just to produce these 8 kilograms to be able to test this motor and these things. But then there are other problems of propagations of radio frequency and everything that really you cannot do that. At some point where you have to go to the moon and test it, because you cannot simulate all the aspects of this very, very complex.
Of course. So the only way is to go there.
Actually,
that's a good point for humans. You know, that's a good point for humans, because we don't want, and this is a philosophical consideration, we don't want to just fill the solar system by automated machines. We want to go to live there, because because we are 8 billion. You know, it wouldn't be of any use to send automated machines and remain enchained to the bottom of Earth gravitational well. So I'm very a supporter of automated machine that can help to prepare the environment for humans to go, and that's the great value of this kind of technologies and the scientific search and so on. This is my opinion, because I am a humanist. So I am in favor of human evolution, that maybe we will become more than humans and things like that. But what I would like is that we can start expanding into space, conserving our physiology more or less as it is, as long as possible, because we know that if we will change it too quickly, that will generate social problems and many things so we hope that we can start expanding, building our environment in the cislunar space and in orbit, using O'Neill infrastructures, going on the surface of the moon just to work, to mine, to produce fuel, and to extract materials, to build the O'Neill cities, because O'Neill cities can have artificial gravity. On the moon, we only have 1/6 gravity, so we will change.
Sure.
So, okay, but however, this consideration doesn't take anything away from the importance and the scientific importance of your
for sure. I think I am very enthusiastic for the first time in my life, in that I think that we really are at the verge of this transformation. You know, when you see a Netflix series and there is somebody that is going with his ship to an asteroid, and you know the ship is broken and he's repairing it with a piece of wire, like if it were in the ground. Well, I think we are going there, really, for the first time. But for that, we need to have economical activity. If we don't have an economical activity, we will never incorporate space really to our society. And I think we are at the verge of that. I don't know if I will see that, but my sons will for sure see it at some point. Yeah.
And we're working for that.
That's
fascinating.
Sure. And that's fascinating.
Definitely. Yes. Definitely.
That's what I think. I think we are like you know, like in 1491, we are at the border of a huge transformation in which a new continent will be incorporated. The continent is the moon, and the ocean is plasma now, is not water.
Yes.
But it is there, and people is unaware, as they should. They probably were also in Europe at that time. You know, you didn't know what it was, but suddenly everything changed, and I think this will happen.
Yeah.
I have another question. One remark. I got a reminder that it will start soon and at 10 o'clock. And I see Einar Larsen is also entering very late, as 1 hour too late. Something is wrong. We have to check it out. But I have another question, Gustavo. You showed me at IAF spring meeting that you are working with balloons. Have you time to show us something or to tell us something about this? So, it would be, because I was really thrilled by what you showed me, and maybe our audience is interested to listen something about this.
Well, I have nothing prepared to show you, unfortunately, but let me just talk a little bit. There is this this area of ballooning, stratospheric ballooning, which is really very interesting. It's very old, if you want. in science, for example, cosmic rays were discovered by Hess from balloons at the beginning of the 20th century. And from there, balloons have been there in science, doing frontier science, large balloons, yeah, in general. For example, we have done together with the French Space Agency and the use of collaboration, which is a collaboration for astroparticle physics, telescope of 100 kilograms that we flew with balloons from Canada to see particles from the stratosphere at 40 kilometers of height. We have done also with NASA another a large one of 4.5 tons that we had flown from New Zealand in a very large balloon, 120 meters. So you can do science with this large balloon. But there is another very interesting thing, and is that you can also use much smaller balloons to go to the same height, 35, 40 kilometers in height, and use it also to do, besides science, to do studies and development of technology for space. This is what is known as, in this case, as quasi-space at this height. So you have many of the problems of going into low Earth orbit, with a difference regarding radiation, basically, which is not such high because the flights are rather short, but all the other things are more or less the same as in space. But you can do it for a fraction of the cost, a very small fraction. And you also have an advantage that if I want to test something for space, and I want to test it in a satellite with a rocket, it will be extremely expensive. It will take a long time to develop. And if I am trying to develop something new, and I made a mistake, or I didn't foresee some problem, well, it will fail, but I will never know why it failed, really, because I cannot recover the payload. But if I go to the stratosphere, I can recover the payload with a parachute and study it and learn what I did wrong, and I can recover it, which diminishes cost, and I can fly it again very fast. And so we use that as a tool also to be able to do with students at a very low cost studies and development of technology. Besides that, it's extremely nice because it's a huge adventure to do that. So students are really, really happy. They can develop a satellite, for example, but which many universities do, a small satellite, but it never flies because it's very expensive to put it in orbit. But we can fly to the stratosphere, and we do it once a month. We go to the stratosphere, and the thing is that they can have all this experience. They can measure, they can everything, and they can participate of the launching campaign, which is really nice because you go somewhere in the middle of nowhere. You spend the night preparing everything. When the sun is rising, you launch, and then basically you can more or less know there are programs that we take into account the currents of air in the stratosphere and can have an assessment and a prediction more or less where it will come, but where it will come down, but you never know. And also, once you cut from the balloon, you are coming down in a parachute from 40 kilometers of height. So basically, more or less, you have an uncertainty which has the same radius of your height, so it's 40 kilometers. So you can fall anywhere. And so it is a campaign in the middle of the mountains and rivers trying to locate the payload and recover it. It's like a Discovery Channel documentary, more or less. So this is really great, and students have a lot of fun with that. And this motivates a lot the people to do things. And also it has another impact. For example, one of the first flights we did in the state of Hidalgo, you can imagine these are regions that are really isolated. Yeah? You have communities of different ethnic groups with their languages and everything in these regions. And suddenly these things come with a balloon, yeah, with a parachute coming down. So it happens the first time it came down in a very, very small village, and we were showing in the GPS that the thing is starting to move. Yeah, so rather slowly, but it was sure somebody had picked it up. No? So we arrived to this very small shop in the middle of this very tiny village. that produced cheese. And the kids in the village had recovered the payload. And they were there with a guy that did the cheese there. And he was fascinated. When we arrived and explained what it was, he suddenly said, "This is the most important thing that happened to me in my life." And so he took a picture and he put the picture in the wall of, it's something amazing. So you are suddenly taking space to places you never imagined. And it's the same with this lunar mission. I have told you all the engineering part, the scientific part, all the context in a larger environment, but go to the people. All these missions have been produced by students. Students that come from everywhere and have studied in this university. And suddenly you have one kid that may have grown in the middle of the forest of Chiapas, in a very isolated village, and suddenly he will see that there is this thing that was done by other young people like himself, and it's in the moon. And it doesn't matter that it is this size and it's only 56 grams. It's a symbol. And the symbol is powerful. It can change completely the life of a person, because fortunately, at least for the time being, when we don't have too much cybernetic things put in our head, intelligent people can be born everywhere.
Of course. It's a pity. It's a pity that Bernard Foing is not with us this night, because he could say something about his experience with the analog training, because he chairs several groups that make analog training for the moon, for Mars environment, and so on. So it's really an interesting experience to work with young people that decide to experiment how they could manage to work on the moon surface or on a Mars habitat and so on. But I still had a question about the moon that I forgot to tell you before. When you say one day, you mean a lunar day. That's about 15 days, 15 Earth days. But when you say that the whole experiment will be made in few hours, you mean the Earth hours.
The
right?
Part of navigation is Earth.
When you say 9 o'clock in the morning.
That was lunar time.
Is the okay? The 9 of the lunar time.
That's lunar time. When I say that navigation will last for 3 or 4 hours, these are Earth hours. Yeah.
Okay. So you will make all your experiment in 1 Earth days, in 1 Earth day, less than 1 Earth day.
Oh, the navigation will be in less than 1 Earth day. It will be 4 hours. Yeah.
Okay.
But then they will keep measurement during the rest of the lunar diurnal day.
So for 15 days.
More, yeah.
And if they survive the night, they can, when the sun enlighten them again after the lunar night, they can start working again.
They can start working. I don't think they will try to move. Well, they will be in a scientific mode, so they will not try to move. But if we turn on the portion that is in the lander, the TTDM could send them a signal to try to navigate. I don't think, even if they survive, that they would be able to navigate, because the motors are not space qualified to that point. Yeah? For that, they would have to be...
they could be ruined by the environment in some way.
They probably can be ruined by the dust.
But another question. Through the lander, can you somehow communicate with the small CPUs of the rovers? So just to take the data in telemetry, or also to say them some way what to do?
I can do everything. I can, during the first part of the mission, which is engineering, I will not interact with them. I will only listen.
They know what to do.
They will be autonomous. They have to do whatever they can. But I will only send at some point the command to change mode from navigation to science.
Okay.
At that point they will do science. But if I want them to do something specific, I can send them commands to try to navigate, to do, I can, I can navigate them like with a joystick. Well, not so easy, but more or less, I can send them out. But say in principle, the engineering part is completely autonomous. That's the key of the question. They have to do it themselves, whether they arrive or not. That's a result. But then yes, we can communicate both ways.
Fascinating. The software engineer that is in me is fascinated by that. I would like very much to have taken part of this project.
Software development is a great fun because they are so small. You have so few capacities that you really have to be extremely efficient. And we were doing this scheme. We do simulations in this environment in which we really simulate like in the video game, but all the electronics is in the simulation, everything. You really program the embedded software there, the motors are there, the solar panels, the rugosity of the soil, everything is there in the simulation, in this like video game. So they work there. They start from different random positions. So we see statistically how the software behaves. With that, we fine-tune parameters on the software. We transfer the software, we embed the software in the real hardware, go to the Regolith, try to do the same in different situations, and see how they differ statistically, and come back to the...
And correct the errors. Yes.
And correct, and you go around.
So you are launching in November?
Well, last quarter, whatever that means. It doesn't depend on us at this point, but I would say yes, at some point between October and December, probably November.
Okay. With NASA? No,
everything is private, really. This is one of these things emblematic of the new space. It's ULA is the launcher, and this will go to a transfer orbit. And then from there is the lander, the spacecraft, that will go from there to the moon. And
I see. Okay. So we'll cross finger, yeah? You will...
Fingers, feet, everything.
No, I mean, when you launch, we would like maybe to participate live to this event. Will it be possible when you launch?
Well, we will certainly be broadcasting.
Okay,
so
great.
We can let you know.
Yeah, let us know. We will put it on our website. So then we can participate and join you in this really amazing project. Gustavo, will you be in Paris in September?
Yes.
So we will. So we will see us again in Paris.
Excellent.
Sure. We can have a good coffee. It will not be Italian, but
Gustavo, it was a pleasure for us to have you here with us, and thank you so much for taking your time and explaining it to us, and it was really, really amazing to have you here. We wish you a nice evening to our audience, and thank you.
Thanks
Thank you very much.
Really a pleasure.
Ad astra.